Welcome back to the Deep Dive. Today we are cutting through the noise to focus on a really interesting architectural shift in foundation model training.
We're looking at the paper LLM-JEPA, Large Language Models Meet Joint Embedding Predictive Architectures.
And if you've been in this space for a while, you know there's this massive divergence in training philosophies. On one side, you have our LLMs. They're all historically rooted in generative reconstruction-based objectives. They live and die by autoregressive token space reconstruction.
Right, which is basically that standard cross-entropy loss, the LLM that we see everywhere.
Exactly. And then on the other side, you have this completely different success story from the vision domain.
Self-supervised learning, specifically with these reconstruction-free methods like JPAs, joint embedding predictive architectures.
And they're fantastic at learning robust, high-level representations, precisely because they move away from that pixel-perfect input space reconstruction.
Yeah, that kind of reconstruction can introduce all sorts of subtle biases. JBs avoid that. They prevent model collapse by forcing a prediction of, say, a different view of an input, but, and this is the key, it's all happening in the embedding space.
So you've got these two philosophies, right? One is all about perfect local detail, like next token prediction in LLMs, and the other is about abstract generalized structure, which is what JEPA does in vision.
And the mission of this paper, LLM-JEPA, is to finally bridge that gap.
Can we inject those superior abstraction capabilities of JPAs into a causal LLM without killing its core generative power?
And the paper's answer is a resounding yes. They propose a JEPA-based solution that works for both fine-tuning and, interestingly, pre-training.
The contributions seem pretty foundational. I mean, they formulated the first JEPA training objective specifically for LLMs that operates on these embedding space views.
And the results were, frankly, decisive. They got statistically significant state-of-the-art improvements across a whole range of fine-tuning settings.
And crucially, they show this wasn't a fluke. It's robust across 4 really diverse, modern model families. We're talking Llama 3, Gemma 2, OpenLLM, and Olmo.
Tests against tough datasets, too. NLRX, GSM-8K, the Spider text-to-SQL task. It's a very thorough empirical validation.
It really gives you confidence this is a generalized improvement to the objective function, not something tied to one specific architecture.
Exactly.
Okay, so let's start by unpacking the math here in section 1. The LLM-JEPA objective itself. We know the baseline is next token prediction, LLM. Pure causal autoregression. So how do they merge that with the JEPA principle?
They introduced a composite loss function, which they call LLM-JEPA. It's really just a weighted sum of the standard generative loss and this new JEPA objective.
So the equation is the total loss equals the sum of LLM plus something else.
Plus a weighted term, lambda, that's multiplied by a prediction function.
Yeah.
And that function is just measuring the distance, d, between the predicted embedding of a text view and the actual encoded embedding of a code view.
Okay, so that first term, LLM, it's like the safety net. It keeps the model grounded, make sure it can still do its main job of predicting tokens.
Right. It preserved the generative capability.
But let's focus on that second term. What's the lambda doing, and what is that distance function, d, really achieving?
Well, lambda is the hyperparameter that really controls the whole thing. It weights how much influence the JEPA term has. If lambda is 0, you're just back to standard training.
And if it's too high, you probably mess with the generative side of things.
You risk it, yeah. The JEPA term itself is what forces the abstraction. It makes sure the model learns a high-level representation of one input, say, the text. That's good enough to predict the abstract representation of a related but different input, the code.
And the core idea from vision, preventing that dimensional collapse, is handled by making this prediction in the embedding space. You're forcing those two representations to align.
Exactly, and the paper found that cosine similarity for that distance metric, d, worked best.
Which makes sense. It's a classic choice in representation learning.
It is, but the real secret sauce, especially for language, is defining what they call non-trivial views of the same underlying knowledge. That's what stops the model from just finding a trivial, collapsed solution.
And their proof of concept for these views was centered on tasks, where you have these paired representations of information.
Precisely. They focused on translation tasks. So text is the natural language request, and code is the structured output.
So, like translating a natural language description into a regular expression, that's the NLRX dataset.
Exactly. Or translating a database question into a SQL query, which is the Spider dataset. These pairs force the model to distill the semantic essence, totally independent of the syntax.
Right. The core concept of find all users older than 30 has to exist in that shared latent space, even if the English sentence in the SQL query look completely different.
That's the idea.
Okay, that makes sense. Let's talk implementation in section 2, because getting this objective to actually work inside the causal architecture of an LLM, that sounds like it required some clever engineering.
It did. They had to define the core components. The encoder, inc, is pretty straightforward. They just use the final hidden state of the last token in the last layer. That's the sequence embedding.
A pretty common practice for distilling a representation.
It is. But the predictor, pred, that's where they got really elegant.
Right, because normally that might be a whole separate, smaller network you have to train.
And to reduce that overhead, they just reuse the LLM's own internal autoregressive weights to act as the predictor. They introduce a special token, PRED, at the end of the input sequence.
And the hidden state of that token becomes the output of the predictor.
Yes. And this weight tying trick is a huge win for computational efficiency. It minimizes the architectural change.
But that brings us to the fundamental technical hurdle. In a normal causal LLM, if you just concatenate text and code, the code tokens can't see the text tokens because of the causal mask.
And even more critically, you need independent representations of both inc text and inc code to even compute the JPA loss without violating the whole principle. Right. If you just concatenate them, the encoding of the second view is causally dependent on the first. It corrupts the objective.
The naive solution would be, 3 separate forward passes, one for the LLM loss, one to encode the text, and another to encode the code.
Which triples your training cost. It's completely prohibitive.
Absolutely. So their solution was this custom self-attention mask.
This is the real engineering novelty.
It is. They
Yeah.
introduced this complex block causal mask. So the mask is causal per block, one for text, one for code. But the 2 blocks are treated as independent segments when you're computing that JPL loss component.
Which means they can get everything they need.
In just 2 forward passes, not 3. And that significantly reduces the computational overhead and makes the whole approach scalable.
Okay, but this brings up the bigger question, the why bother question. Why go through all this trouble? Doesn't a big LLM trained just on next token prediction implicitly learn strong enough abstractions to connect text and code anyway? That was the crucial empirical test, and the paper gives us the smoking gun. They show that minimizing the standard NTP loss, LLM, does not implicitly minimize the JPA prediction loss.
So they tracked it.
They tracked the JPA loss over time for a standard baseline model, and it just stayed flat. But for the LLM-JEPA model, that JPA loss was dramatically minimized.
So the standard objective just fails to drive that specific abstract alignment. You need the explicit JPA term to boost the representation quality in a way NTP just overlooks.
And what's more, they confirm that adding the JPA term didn't hurt next token prediction at all. The LLM losses for both the baseline and their model were basically identical.
So you're injecting this structured learning without any trade-off to the core generative skill.
Exactly.
Which brings us to section 3. And the empirical results really do validate this. The fine-tuning superiority seems to be across the board. We're not talking small wins here.
No, these were statistically significant and very consistent improvements. But what I found even more compelling than just the peak accuracy was the robustness against overfitting.
All right, that's figure 1.
Yeah. You look at the 6 training epochs, and the standard fine-tuning model shows that classic overfitting curve. Accuracy peaks around epoch 4, and then it starts to decline as it just memorizes the training data.
But the LMU-GPA model just doesn't do that.
It doesn't. Its accuracy continues to climb, or it stabilizes, even through epoch 6. It shows this superior resistance to overfitting.
Which suggests the GPA objective is acting as a really powerful regularizer. It's forcing the model to generalize instead of just memorizing syntax.
I mean, that has huge practical implications for anyone deploying these models, where you're often fine-tuning on smaller data sets.
And the practical side continues when we look at parameter-efficient methods like LoRa. For practitioners, this is all about cost control.
And it's a major advantage. With LoRa, LLM-GPA converged faster. But crucially, they found that an LLM-GP model fine-tuned with a pretty modest LoRa rank of 512. It achieved an accuracy that was comparable to the full fine-tuning performance of the standard baseline model.
Wow. So you get the performance of a full fine-tune for the cost of a parameter-efficient run. That's a huge deal.
It is.
Now, before we get to the why, what about the ablation studies? They tested other things, right? Like using L2 norm or MSE instead of cosine similarity?
They did. They also tried replacing the predictive loss with InfoNC, which is obviously very popular in contrastive learning.
And what was the takeaway?
The takeaway was that their specific design choices matter. The proposed configuration with cosine similarity was clearly superior. It's fascinating, actually, that InfoNC performed so poorly.
That is counterintuitive. Why would InfoNC fail here? I mean, it's designed to push different representations apart while pulling similar ones together.
It seems that the constraints of the causal LLM architecture, combined with how these views are defined, might make InfoNC too strict or maybe just unstable. The simple direct prediction objective, just minimizing that cosine distance, provides the right amount of gentleness and stability for this specific setup.
Okay, let's dive into the most compelling part for me, Section 4, the why. How exactly does this new loss function create these better representations? It all comes down to the latent space.
Absolutely. The TSNE plots give you the qualitative proof right away. When you visualize the embedding space, the standard NTP fine-tuning often just disrupts the nice clustering that was already present in the pre-trained base model.
It's prioritizing local token prediction over any kind of global semantic structure.
Exactly. Whereas the LLM-JEPA fine-tuning does the complete opposite. It induces what they call a nice structure. It organizes the text and code representations into these coherent, tight clusters.
So you can literally see the semantic alignment.
You can, but the quantitative analysis using linear algebra is where the real insight is.
They hypothesize that LLM-JPA is enforcing this structure by constraining the transformation from the text embedding to the code embedding, forcing it to exist in a much narrower, lower dimensional subspace.
That's right. And to test that, they use singular value decomposition, SVD, on the difference matrix between the two embeddings. If that transformation is constrained, the difference matrix should be low rank.
Meaning its singular values should drop off really fast.
And the results were just stark. Orders of magnitude different. The sum of the top 100 singular values for the LLM-JPA models were dramatically smaller down in the 16 to 94 range.
Compared to what for the baseline?
Over 310. This is the mathematical proof of a kind of geometric compression. LLM-JPA is forcing these two views into a much simpler, more constrained relationship in the latent space.
And the theoretical consequence of that compression is this idea of a near-linear transformation between the views.
Yes, which they also confirmed. They quantified the error of a simple least squares regression trying to map the text embedding to the code 1. For the baseline model, the error was in the thousands. It was a chaotic, nonlinear relationship.
Okay. And for the LLM-JPA models?
The error just plummeted. It went down to between 4.04 and 4.47.
From thousands down to single digits. That's incredible. It strongly supports the idea that the relationship becomes almost linear.
And that simplified, structured mapping is likely the direct mechanism behind the model's increased robustness and accuracy. It's the ultimate proof that the objective is doing exactly what it was designed to do.
It's the highest form of synthesis, really. The model is learning an abstract concept that's transferable between views through a simple, recoverable math transformation.
Precisely.
This all sounds incredibly powerful for text-to-code tasks, but let's shift to Section 5. What about generalization and, of course, the computational cost? Does this structural boost apply beyond that explicit text-to-code paradigm?
It seems to. They tested generalization on broader tasks. For example, the NQ OpenQA benchmark. The text was the question, and they treated the answer span as the code.
Right.
They also tested HelloSwag, which is a context completion task. And in both cases, LLM-JPA showed statistically significant improvements over the baseline. They even showed it worked on larger reasoning models like Qwen 3 and DeepSeek.
So the structure it learns on code-like pairs actually generalizes to improve reasoning and comprehension.
It confirms the benefits are universal, not scale-dependent. But we have to address the cost. The primary limitation here is the computational bottleneck.
Right. Because you need that extra forward pass for the JEPA loss, the training cost basically doubles.
Approximately, yeah. A twofold increase in training cost is a massive barrier if you're thinking about scaling this to, trillion parameter models.
So how do they get around that? How do you make this feasible for pre-training?
They introduced a strategy called loss dropout, or LD. It's a simple but really effective idea where you just randomly drop the loss term during optimization at some specified rate, alpha.
So if you set LD to 0.5, you're only computing the expensive part half the time.
Right, which brings your average per epoch cost down to about 1.5 times the baseline, not 2x.
And the surprising finding was that it works really well.
It does. LLM-JP can tolerate aggressive dropout rates, even up to 0.75, and it still converges faster. and achieves higher accuracy for the same total PFLOP's budget compared to the standard baseline.
So that's the key to making it computationally feasible for scaling.
It is. They found a sweet spot where you get the structural benefits without paying the full 2x penalty, and they even offered a helpful heuristic for tuning. Keep the term lambda times 1 minus alpha approximately constant.
Okay, so wrapping up this deep dive, LLM-JP really feels like a monumental step. It successfully imports the structural benefits of vision JPAs into the causal LLM architecture, and it does it while preserving those crucial generative capabilities.
The key insight for me is the quantifiable power of using these explicitly defined views of knowledge to impose structure on the latent space. That SVD compression, the confirmation of the near-linear transformation, it shows you exactly how it's outperforming standard NTP, which tends to disrupt that global coherence.
The work provides incredibly strong evidence for fine-tuning, and the preliminary pre-training results were also promising, which points a way forward for foundation model development. But the authors do highlight a challenge. LLM-GPPay adds hyperparameter complexity. You have the GPK, lambda, and the predictor token count, K. And the optimal grid points for these seem pretty scattered, which means a high tuning cost.
Which leaves us with a critical question for the future of scaling this. If LLM-GPay is going to be used for the full pre-training of truly massive models, where these hyperparameter searches are prohibitively expensive, what kind of automated or adaptive mechanisms will we need?
You mean things like adaptive lambda schedules or maybe dynamic ways to determine the optimal predictor setup?
Exactly. What will be required to navigate that complex hyperparameter space efficiently and ensure convergence without incurring an unsustainable tuning cost? That, I think, remains the next frontier in making this a truly universal paradigm.